So now we're going to start with a different type of problem. So this problem that you are seeing on the screen is talking about a table that shows the births of babies at a Brisbane, Australia hospital on a particular day. And we are going to construct a relative frequency distribution of the number of girls and boys born. So this is what we have done in chapter 2 at the beginning of the semester. So let's finish that. So I'm going to say first the categories are boys and then it is girls. And the way I'm going to answer this question is first finding the frequency and then finding the relative frequency. So say frequency and relative frequency. So it's basically counting. So girls, I will say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the frequency for girls is 18, and then we do it for boys, and that will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So the total is going to be the sum of these two, which is 44. Hence, when I'm finding the relative frequency, I'm saying it's 26 over 44. And that is going to give me 13 over 22. And this is 18 over 44. And that should give you 9 over 22. So what we can say that writing in terms of decimal number, we can divide 13 by 22, round to 4 decimal places. That will be 0.5909. 0.5909, and hence this one is going to be 0.4091. So then what we will do, we will use the relative frequencies to construct a probability model. And that's very simple. All you need to say is that probability of boys is equal to 13 over 22, or you can say 0.5909 in the decimal format. And probability of girls is equal to 18 or 9 over 22. I think that's what we used. 9 over 22. And that should be equal to 0.4091. Now to check that it is the good probability model, we will say probability of boys, as you can see, this thing is between 0 and 1, so satisfies the first criteria. Also, probability of girls is also between 0 and 1, so satisfies the first criteria. The second criteria, probability of all the outcomes, so probability of boys plus probability of girls when added, probability of all the outcomes when added should be 1. So let's check that. 0.5909 plus 0.4091 should be equal to 1. So that satisfies the second criteria. So this is a perfectly good probabilistic model. And these type of assigning probability will be called the relative frequency method of assigning probability, which we are going to use when there is no human factor involved. Confirm that your probability model follows the rules of probability. We have done it in the last part, so I will just say check part B. All right, let's go to the next problem. Picnic lunch. Picnickers at the 4th of July fair have the following preferences for grilled lunch: cheeseburger 50%, hot dog 25%, veggie burger 25%. Consider the experiment of 2 picnickers chosen at random, choosing their preferred lunch. Construct a tree diagram for the experiment. What is the sample space? So again, it is the question of a tree diagram, and because we are doing it for 2 picnickers, I will say we can do it in this way. So picnicker 1, I'm just going to call it P1, and picnicker 1 has 3 choices. it has the choice for cheeseburger, so let's call it CB for cheeseburger, or hot dog, so HD, or has the choice of veggie burger, so VB. For that, picnicker 2 can choose cheeseburger, hot dog, veggie burger. Similarly, picnicker 2 can choose cheeseburger, hot dog, veggie burger. And the choice is, when the first picnicker has chosen veggie burger, the second picnicker has still 3 choices: cheeseburger, hot dogs, and veggie burger. So there are a total of 9 elements in the sample space. It asked me to write the sample space, so we'll go ahead and say S is equal to cheeseburger, 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 hot dog, cheeseburger, veggie burger. That's when the first picnicker has chosen cheeseburger. You can also do hot dog, cheeseburger, hot dogs, veggie burger, or hot dogs, hot dog should be the next one, and hot dog, veggie burger. And then finally, if the choice is veggie burger for picnicker 1, the second picnicker can choose cheeseburger, veggie burger, hot dog, and veggie burger, veggie burger. And these are all the 9 choices, giving you the sample space. A similar tree diagram question again. This time, video games. The following percentages of students at a local high school express preference for the following game consoles. PlayStation 3 of the 3, 40%. Xbox 360, 35%, and WII 25%. Consider the experiment of choosing 3 students at random. Construct the tree diagram for the experiment. What is the sample space? So this time 3 students, so it will be easier if we do the horizontal table. So we'll say student 1, they have 3 choices, as I can say PlayStation, Xbox, and this is for WII. Now for the second student, you have 3 choices if the first student has chosen PlayStation. So PlayStation PXW. Similarly, if the first one is X, then you have 3 choices P, X, and W. If the third one is the first one is W, and you have 3 choices P, X, and W. That's student 2. Remember, I have one more student, and again I have 3 choices. So I will go ahead and do that for each situation. PXW, PXW, PXW. This one, I'm going to use a different color so that I don't confuse myself. PXW, PXW, PXW. And finally, we will get PXW, PXW, PXW. And this is the way that you should write the sample space, because sample space counting can be a very challenging process if you have, say, 5 students. Then having the tree diagram is going to help you write down the exact sample space. So I'm going to try to write the sample space. As you can imagine, I have to write 27 different things. So I will say P, P, P. Then I can say P, P, X, P, P, W. Then I will go ahead and say P, X, P, P, X, X, P, X, W, P, W, P, P, W, X, P, W, W. So I'm exhausted with P. Now we will do X first. So X, P, P, X, P, X, X, P, W, X, X, P, X, 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 W, XWP, XWX, and XWW. And finally, we're going to start with W, and I will say WPP, WPX, WPW, WXP, WXX, WXW, WWP, WWX, WWW. And these are the 27 outcomes in the sample space answering my question. Rainy days. Students at the local middle school have been keeping track of the number of days it has rained. In the past 100 days, it rained for 33 days. What is the probability that it rains on a randomly chosen day? So it rains on a randomly chosen day. I will say probability, and let's use the letter R for it rains. So I will say probability it rains. So let me just describe it. It rains should be 33 out of 100. So that's 0.33 in the probability. That's the first part of the question. The second part of the question is, what is the probability that it doesn't rain? So let's call it NR, stands for the event does not rain. Now I am using NR, you can use any letter. You just have to describe what you are meaning by that letter and then find the probability. So the B, second one, is probability it didn't rain. If 33 days it has rained, then 67 days it didn't rain. So it's 67 over 100 and then 0.67. The last part of the question, which method of assigning probability did you use? We used, remember this is the relative frequency method. We used the relative frequency method. And why did you use the relative frequency method? Because this is such an experiment that will change depending on the geographic location. For example, if you are in Seattle rainforest, it is raining constantly. Versus if you're in Arizona, in the desert, it is not going to rain as much. So I have to use the relative frequency method. So we use the relative frequency method as outcomes might not be equally likely. It can be biased depending on other situations. This example is talking about illegal parking. We talked about this scenario before. Suppose you find that 10 out of 50 cars parked in handicapped zones are parked illegally. You would like to find the probability that a car parked in the handicapped zone is parked illegally, explain whether or not you can use the classical method of assigning probability and why. So, no, we should not use classical method. And I'm pretty sure you understand why we should not be using classical method, because this experiment doesn't have equally likely outcomes. It changes depending on the location of the parking lot. The outcomes might not be equally likely. So as a result, we're going to use the relative frequency method. So the second question is asking you, find the probability that a car parked in the handicapped zone is illegally parked. So I will say probability of, say, illegal parking, so probability of IP, say, and I will just say IP stands for illegal parking. Because I know out of 50 cars, 10 are parked illegally, I will say that this is as simple as 10 over 50. So that's 1 over 5, or you can say 0.2. Which method did you use? We used the relative frequency method. The last problem in this section is asking us about a poker hand consisting of 5 cards, and from the standard deck of 52 cards, this hand is dealt. find the probability that the hand contains 5 hearts. So what we're going to do with this problem? Remember, for the first card, when the hand was being dealt, there are only 13 hearts. This is the first hand. 13 hearts and a total of 52 cards. So that's the probability for the first card to be heart. What is the probability for the second card to be heart? Well, if you have chosen one of the hearts already, then there are 12 of them left. And there are 51 total cards left. So this is your second card, that is heart. Then I do third. And this time, you have 11 of the hearts left because 2 of them are chosen as the first and the second one. But there are total 50 cards as well. Then the fourth card, and probably you can understand the pattern, I have 3 chosen, so there are 10 hearts out of a total of 49 hearts left. And then finally I do the fifth card, and that will be 9 of the hearts are left because 4 are chosen out of a 48 total cards. And the probability is going to be the product of these individual numbers. So we can calculate this number in our calculator and round to 4 decimal places. So for the top, I do 13 times 12 times 11 times 10 times 9. And then I divide it by 52 times 51 times 50 times 49 times 48. So I get something around 0.000491. So this E minus 4 stands for 4 decimal places. So since this number is 4.9 in scientific notation, when you have E minus 4, you are supposed to move the decimal point 4 places to the left. So if I move it 1 place to the left, I go to the left of 4. I still need 3 more places, so I will need to put 3 zeros. So that's why I said 0.12304952. So that should be equal to 0.1234 and 592, I think was the answer. 4952. 4952. Answers my question for the probability. And next time we will start talking about inclusion exclusion principle and arithmetic of probability.